Thank you. Yes.
So thank you very much for inviting me. As you see from the title, we talk about computational medicine, and more specifically on heart simulation. And I will try to address, at some extent, both issues of physics-based models and models based on data-driven algorithms, say. Let me start from the very beginning. This is a picture that tells you how we have been motivated by this research. We want to start from clinical problems and hopefully try to provide answers that are of interest for the doctors, for the medical doctors. And we go through the classical path of applied mathematics. We start with the pre-processing phase, where we try to analyze the data that should be then available for the model. Then we go to the mathematical model, and then to numerical methods to approximate them, and in the end with the simulation, and try to say compare the results of our simulation with those of the clinical environment, and hopefully find a good agreement between the two approaches, say, the two set of data. So this is the global picture. And let me very quickly go through the pre-processing just to mention the phases. We typically start from images, those that are available. Then we go through the segmentation of images, through their registration in case they are taken at a different time. Then we have to create a mesh, which is first of all a superficial mesh, and then the volumetric mesh. And then we reconstruct the fiber in the heart that are seldom available. And this is preliminary to use the mathematical model, say. So we use virtually any kind of data available, going from computer tomography to cine MRI, magnetic resonance, late gadolinium MRI, and phase contrast MRI. And we use them for multiple purposes. We use a CT scan to reconstruct the shape of ventricles or a coronary, say. We use cine MRI to find, in some cases, the motion, for instance, of the ventricle, the external motion of the ventricle. We use late gadolinium enhancement to find the regions of the ventricle where there are possible, say, scars, which are the black areas that are no longer conducting the electrical signal. And we use phase contrast MRI to generate boundary conditions. Very often we do not have boundary conditions, we do not have initial conditions that are important for our models. So this is a kind of very quick picture. And let me conclude this very first section very rapidly by mentioning the problem of the fibers. Fibers are very important because they allow, from one side, the propagation of the electrical signal, and the other side, due to their torsion, they allow the myocardium to contract and to relax. And the fiber distribution is not very often is not available from clinical data. So we need to use some mathematical models that are based on solving the Laplace equation with the different kind of boundary conditions in order to reconstruct the transmural direction of the fibers, say. So the orientation of the fibers in the epicardial, which is the external part of the myocardium, are in a given status, and then they change their direction across the myocardium until the endocardium, and you want to reconstruct these say variable directions of the fibers and of the collagen sheet. So this is preliminary to the use of the model, and then we need to develop a model. And first of all, we need a conceptual model. And in this conceptual model, as you see, there are all the components of the physical processes that take place in the heart. So we start from the electrophysiology. We have the cells in the sinoatrial node that undergo an excitation, and we take this as a data. So this is our starting point, say, and from there we generate an electrical field that propagates first on the upper part of the heart, namely the two atria, and then down to the lower part of the heart, to the apex and to the whole myocardium. And we analyze what happens at the cell level, where we have the opening and closing on the channels, and through the channels there are ions of calcium or potassium, say phosphorus, that go back and forth, and they create an extracellular potential. And this extracellular potential is triggering a force, which we call the active force, that is generated there, and is the one that is due to the sliding of the cross bridges. And from then, we pass to the tissue mechanics, where we solve problems for the mechanical deformation of the whole myocardium. Then we go to the blood dynamics, and the blood dynamics means that we are investigating the fluid dynamics at the atria level, and say within the atria and within the ventricles. Then we have the opening and closing on the valves. We have the perfusion of the myocardium thanks to the coronaries, and then we have the propagation of the electrical field through the body and reaching the torso, where you can get electrocardiograms and reconstruct numerical electrocardiograms. As you see, of course, there are connections between all these blocks, with all these physical processes, and these connections are expressed here by those quantities that are exchanged between the different blocks. So as you consider this as a global conceptual representation of the heartbeat, and we try, of course, to express this through equations. So this is a long process, and most of what you do is known in the literature. Something is new, and we have developed all these models, and ending up with, say, a synthetic picture, which is this one, which embodies, which represents the most important equations that we have to consider. As you see here, the block of the electrophysiology, where we have partial differential equations in terms of the transmembrane potential V, and those are nonlinear reaction diffusion equations. They are coupled with what happens at the cell level, where you have the dynamics of the ions, and the coupling is through the you see this reaction term. So this is a system of partial differential equations. It's called the bidomain model, coupled with a system of ordinary differential equations. Sorry about that. Now, this is the fourth generation, how you generate the force due to the extracellular, to the transmembrane potential. And at the end of this, you see, this system, this global system, allows us to reconstruct S, and S is the, say, elongation of every single cardiomyocyte, basically. We need to assume that there is a Cauchy stress, an active Cauchy stress, which depends on the elongation of the cardiomyocytes, but also on the deformation of the whole myocardium. And as you can see, this active stress depends on three coordinates: the fibers, the sheets, and the normal to the sheets, basically. Then you have the solid mechanics part. We want to compute D. D is the displacement of the myocardium, and we do it by solving this equation, which is a kind of classical equation of mechanics, where you have the equilibration of forces here. And you see you have a second order derivative with respect to the time. For D, you have the density of the myocardium, you have the divergence of the Cauchy stress, and the Cauchy stress in this case is the sum of two components. One is the active component that you have seen before, which is due to the electrical field, and the other one is what is the classical, say, Cauchy stress. We call it passive Cauchy stress, which is the one that you find in any possible, say, solid structure. Then you have the fluid dynamics. The fluid dynamics, we have in Navier-Stokes equations for incompressible viscous fluids. In as you see here, this is the momentum equation in the atria and in the ventricle. U is the velocity field of the fluid particles. P is the pressure. And here you have an extra term because you want to account for the presence of the valves. So we call this the RIIS, which is the resistive immerse method, say, that we use to account for the presence of the valves. And please take into consideration the fact that we are solving this problem in a moving domain, because the chambers of the heart are not fixed, they are deforming, and the deformation law, of course, is not known, is an extra unknown, and so those equations should be solved in a moving domain, and this is why we need an extra equation to reconstruct, say, the actual geometrical shape of the chambers at any given time. Then we have the perfusion of the myocardium, where we account for the large arteries, the large coronaries that are sitting on the external part of the myocardium, called the epicardium, where we solve Navier-Stokes equations. But then we have all the ramification in the small arteries, in the small coronaries that enter the myocardium, and we account for very many of them, order of 80,000 of them, and we use a kind of a Darcy model with different scale. It's a multi-scale Darcy model to account for the perfusion of the myocardium. We have to close this system by two further equations. One, which, say, allows us to compute the propagation of the electrical field across the body and up to the torso, to external surface of our body. And the second one is the, say, the connection with external circulation. So this is a closed loop system that we solve in order to find, say, simulate what is going on in our heart. For those of you who could be interested, these are some references to the, say, to the literature, to what we have been doing in this field, in different sub areas for the cardiac fiber generation, for the generation of the active force, for the electromechanics and the circulation, for the hemodynamics, so the fluid dynamics, for the fluid structure interaction, for the perfusion, and for the torso potential.
So,
you can
Professor Quarteroni, so there are sort of 7 parts of the modeling, and what are their timescale? Are they similar timescale or very different?
Yeah, very good question. I think I will address this issue in a little while, if you don't mind.
Okay, please. Great.
Yeah.
Thank you.
Sure. But please know that if you are interested, you can get all the reference here. And if you scan this QR code, you can get all the PDF of the papers. Say. So this was the modeling, and now we need to go to the numerics. And here, basically what we have to address is how do we approximate those mathematical models? So which kind of numerical methods we use? How do we couple the different components of all these physical processes? We need to stabilize, as we see, and we need to use suitable algebraic solvers for parallel computing. And we had to develop a scientific library to solve all these problems, of course. So those are the main steps. And let me just mention, without giving any detail, let me just mention the most important, say, features. The first one is what can be called the multiphysics. Why multiphysics? Because you have different type of physical processes, as I've told you, with different parameters, different say characteristics of the differential equations. We have both partial differential equations and ordinary differential equations. Most often are nonlinear and they are strongly coupled. The second condition is what Professor Kim was mentioning, namely the multi-scale nature. We have many different scales, both in time and in space, actually. In time, because the characteristic time of the propagation of the electrical field, this is much quicker than, for instance, the characteristic time of the mechanical deformation and also the fluid dynamics. So we need to use different time scales, numerical time scales, to take into consideration these multi-scale processes. We have to approximate our different variables with the different, say, finite elements or spectral elements or isogeometric analysis, different type of numerical methods that are living on different grids and that are expressed by polynomial degree of different orders. So we need operators that can easily go from one grid to the other and from one, say, polynomial degree to another polynomial degree. And they should be very quick in order to be affordable. When we solve the problem, we have different approaches. The classical approach would be to use what is called a monolithic approach, which means that we take the global system after the discretization, after the approximation, and we try to solve it all together. This would be great because it would allow stability, but it's hardly possible because of the size and because of, say, the computational time that you need and because of the memory storage that you would need. So what you typically do is to separate the different pieces and which means the different physical components. And you can do it in many different ways. One way is to use what is called a partitioned approach. You subiterate between the different physics for any given time step until convergence. This is one possibility. Another possibility is that you do not subiterate, but you solve first one process and then the other, and then the other, and then the other. And then you can use, as was mentioned before, different time steps for the different processes. So you have to make different time steps on a single process before moving on to the other process. And of course, every time you use this type of approaches, you have two different numerical problems. One is convergence of the subiterations, and the other one is that you are introducing an error, which is a splitting error. And you may have instabilities that are due to the splitting because the global physics is all coupled, and here we are artificially splitting it. So you may need to stabilize it by suitable algorithms, and this is not easy. Then you need to linearize your problem. You need to linearize because you have a nonlinear algebraic system of equations, and we use different kind of techniques, the classical Newton or quasi-Newton or inexact Newton or fixed point iteration or fixed point acceleration methods and many others. And this again is a difficult issue because you need to use linearization techniques that are convergent. And you know, Newton is second order convergence, a second order convergence, but you need to start very near to the root of the problem, to the solution of the problem, which is hardly known. So that's why you typically go to quasi-Newton, Isaac Newton, or fixed point iterations. And typically you have to combine all these methods in order to make sure that you are actually converging. Then you have to you solve by iterative methods, and typically use conjugate gradient methods for say, symmetric system, or GMRS, or BICG stab, or MinRes, for non-symmetric systems. And then last but not least, we need to develop parallel preconditioners, which are based on multi-grid, algebraic multi-grid, or domain decomposition methods, because we need to look for scalability, meaning that when you're using multiple processors, we want to make sure that our time, computational time, get reduced proportionally, and which again is not an easy task. If you have any question, please feel free to ask questions. Okay, no problem for me. Right. So to do all this, we have developed our own library, scientific library, which is now accessible. So if you are interested in solving problems on the hard context, the library is not only for the hard, it's for partial differential equations in general, but it has been conceived, say, having in mind specifically application to the hard. So it's in C++, and it has large-scale parallel computing capabilities. It is called LifeX, and if you are interested in using it or just looking at it, and you need extra information, please feel free to contact us or to use it. So with this, we can start our simulations, and we can address all the main, say, physical processes. This is the electrophysiology. We compute, as you see here, the transmembrane potential. This is the scale. We go from -80 to +40 microvolt. I'm sorry, millivolt, and for the ventricles, and we go from -80 to +20 millivolts for the atria. So as you can see, you start here with excitation at the sinoatrial node. It propagates first to the atria and then down to the septum, reaching all the cells of the ventricle. What you see on the right-hand side here, I hope you see my mouse, you see the you see the electrical front that is propagating, while on the left-hand side, you see the so-called activation map, which is very familiar to the doctors, to the medical doctors, where you have isolines that are connecting the points that have been activated at the same time. Then we go to the mechanical part. This is the active tension. The active tension is the one that is generated at every single cardiomyocyte due to the electrical field. And you see the heart beating. Maybe you see it again. Let me see. All right. You see it again. And you see the synchronized action of the beating heart at the microscopic level, say, at the cross-bridge level, say. Then you have the macroscopic, the global beating of the heart. Here you see a complete view. What you see here in the middle is the displacement. We go from 0 to 2 centimeters. 2 centimeters is a large displacement. Remember that the heart, typical dimension of the heart says or the order of 8 centimeters. So this corresponds to the 25% of the displacement. What you see here is on the left-hand side is the velocity field. And you see different colors refer to the values of the intensity value of the velocity field, and you see similar view here on the right-hand side. This is the fluid mechanics, and you see the action of, first of all, you see the heart beating here in the torso, and what you see here is the presence of the valves. This one is the mitral valve, the one connecting the left atrium with the left ventricle. Then this one is the pulmonary valve, which connects the right ventricle with the pulmonary artery that is bringing venous blood to the lungs. And then this blood, once it is oxygenated, it returns back to the heart through 4 pulmonary veins. It goes in the left atrium, and then from there down into the ventricle. And when in the systolic phase, when the ventricle shrinks, this is ejected into the main aorta, as you can see here, through a valve which is hidden here, which is called the aortic valve. So you see the typical velocity the typical velocity, you go from 0 to 1 meter per second, which is order of, say, 36 kilometers per hour for a regularly beating heart, say, so for an healthy heart. Now, you can show that the different processes are actually connected together, and here is an example. This is a patient with atrial fibrillation. This is the left atrium, and we are injecting artificially blood particles, and we want to see how many of them are still in the left atrium after 6 heartbeats, right? So this is what you see on the left hand is an healthy patient, and what you see here is a patient with atrial fibrillation with increasing severity. And what you see is that for the highest severity, after 6 heartbeats, there will still be the 12% of the particles in the atrium, while for an healthy patient, you only have the 3% of the particles in residence. So it's 4 times higher. And this is important because it basically explains a possible relation between the fluid dynamics and the electrical rhythm for patients affected by atrial fibrillation. This is the last picture that I want to show is the perfusion of the myocardium this is in the pressure in millimeter of mercury, and you see first of all the electromechanics and then the fluid dynamics, and this is triggering the perfusion through the say the epicardial coronaries, and the small coronaries that you cannot see here, but they are inside the myocardium, and they are modeled by this multi-scale say Darcy model. Now we have been addressing many critical problems, so I will be very fast on that because I don't want to take too much of your time, but just to give you an idea of the type of problems that we are addressing together with different medical doctors: coronary artery diseases, valve dysfunction, aortic aneurysms, arrhythmias, cardiomyopathies, heart failures, and also the effects of COVID-19 on the cardiac function. So these are examples of, say, applications that we consider with medical doctors. And again, here are hospitals with which we collaborate. And here are, again, indication of possible papers where we've been addressing the atrial fibrillation, the ventricular tachycardia, the hypertrophic cardiomyopathy, and the transaortic valve implant, the perfusion, the mitral regurgitation, and so on and so forth. And here, if you scan, you can again get access to the PDF papers, sorry, to the PDF version of the papers that stand at the basis of this research, say. Now, I'd like to give you an idea of how long it takes for a single heartbeat simulation. We are using around 20 million degrees of freedom for partial differential equations, about 30 millions of degrees of freedom for ordinary differential equations at the cell levels. We're using 16,000 time steps for a single heartbeat, which means that, as you see, is a very, very, very tiny time step, because we want to actually address the complexity of all physical processes. In total, for a single heartbeat, we're using 700 billion of variables, 700 billion of variables. We solve the problem on a supercomputer. We are using 1,100 cores, and this takes for about 4 hours. So very long time for a single heartbeat, as you can see. Of course, it's costly because you need to use a supercomputer, it's ordered to 2,000, say, dollars. Euros or dollars are about the same. It's very consuming in terms of energy, right?
Yeah.
And also it's very polluting because we are using extensively the computational time. So mathematics is not really green. See, when you go through applied mathematics, of course, if you write theorems, or if we just work with paper and pencils, it's fine. But otherwise, if we use computers, we have to be aware of the fact that we need to improve our models in order to be more efficient, taking less time and more accurate, right? In order to have a carbon footprint which is the least as possible. And this is where artificial intelligence enters into the business. And I would like to be quick on that, but just to give an idea on the way we are using artificial intelligence in our approach. And let me first mention that in the past century, in the 20th century, all the scientific, development were based on three pillars. The theory, which is the one that gives us fundamental equations, right? Those that are there forever, that you never change, that are invariant in space and time. The experiments, and then the simulations since the middle of the past century, since von Neumann with the computer side. So these were the three pillars of the scientific development. And today we have a fourth pillar, which are big data. We have big data that's generated everywhere. And we developed then artificial intelligence algorithms that we'll talk about in a little while. And this is the main goals, to develop artificial intelligence algorithms together with physics-based models. We want to use them together, not alternatively, right? We want to use the computational time, the computational complexity. We want to address the variability, the shapes, different arts, noisy data, forcing terms, and go to the population analysis. To go through uncertainty quantification, we want to quantify the uncertainty that we have on data and on the model coefficients. We want to identify parameters and carry out sensitivity analysis. Sorry. Okay. We want to derive reduced order models in order to have, instead of the 700 billion variables, to have 1,000 variables, or say 10,000 variables. We like to learn models when we do not know models from physics, and hopefully to go to real-time analysis to better interact with medical doctors. So we basically use for that artificial intelligence algorithms, and we use them in a synergistic way with physics-based models. So what you see on the left-hand side here is all what I've been doing so far with the physics-based models. On the right-hand side, we have algorithms that are based on artificial neural networks, essentially. And we exploit the interrelation between the two approaches. And this is what today we can call scientific machine learning or mathematical fusion between the two approaches, and with multiple purposes, as I was mentioning before. And again, you may have an idea, if you are interested in this field, if you can scan this QR code, you will see our contributions to the field, which is summarized here in a very quick manner. And again, you can go to the QR code and scan. We want to address the geometrical variability, the state variability, to reconstruct the dynamics of non-Markovian dynamical systems when they are not known. We want to use multi-fidelity physics-informed neural network to estimate unknown parameters in our model. And we want to develop reduced order models to enhance the computational efficiency of our approaches, say. And in all those cases, we are actually combining the physics-based models with the artificial neural networks. Here are a few examples, but again, you can go to the QR code and try to have access to the papers. And if you are interested in those problems, let me say that from a modeling point of view, we are trying to go beyond the heart and first of all extend to the pulmonary circulation, to the lungs, and we did it. We started with the COVID-19, where we know that we have in the COVID-19 patients higher resistances, higher pulmonary resistances, and lower saturation of the oxygen. So we try to account for this change of system and to see the impact that this has on the cardiac physiology set. In particular, to see on the, say, right part of the heart, where you have to do more work in order to contrast the increase of the pulmonary artery from one side. So you change the mechanical feature, the mechanical functioning of the right heart. And on the other side, since you have less oxygen to bring to the cells, the generation of the active force should have to take into consideration this reduction of the active of the oxygen. We started also with Professor Antonietti at MOX, the analysis of the brain, of the modeling of the brain. And here there are many different aspects we are interested in. One is the cerebral circulation. The other one is the implant of prosthetic devices to cure aneurysms, for instance. And again, developing model for disorders like Alzheimer or Parkinson, generally speaking, neurodegenerative diseases. Of course, this requires to furtherly generalize the model that we have seen before, and we are not yet there, but we will have to couple this with the metabolic, with the model of the metabolism, and try to have a broader picture of what's going on at the system level. I think I still have a few minutes.
Sure.
Okay. I'll try to be fast and just give an idea of which are the some of the problems that we are facing when we are using artificial intelligence algorithms. And I'm just thinking with the mathematical part. One problem is which is the role of parameters and hyperparameters. As you certainly know, when you develop artificial neural networks for machine learning, you have layers of artificial neurons, and how many layers do we use and how many neurons per layer? These are what are called the hyperparameters. And these are design principles for the neural networks. But then you have parameters. You have parameters that you have to use within each neural network to simulate biological networks. So how do we choose the parameters? How many parameters do we use in our model? How many hyperparameters? These are constructive criteria, and we need to better understand their roles in the constructive phase. Another aspect is that when once you have decided how to build up your network, you have to find the parameters and the hyperparameter that minimizes the loss function, namely the discrepancy between what you are predicting and what was true in the set of validating testing data or validation data, say. So you have to minimize loss functions that depend on many parameters, sometimes on hundred or thousand of parameters. Those are typically non-convex functions that you have to minimize in very large spaces, and finding algorithms that provide convergence, that ensure convergence is not obvious at all. And there is a lot of debate and also new methods. For instance, you have stochastic minimization algorithms, and we need a better understanding of their convergence properties. How to guarantee the success? Sometimes these neural networks provide excellent answers to our problems. Other times they do not. They are not able to give answers that are acceptable. And what is the reason? Well, which is the role of training data set, validation data set, and testing data set. This has to be understood on mathematical ground. And then there is the issue of explainability. How is a certain decision reached, right? I mean, how can you go into the algorithm and try to understand the way the algorithm behind artificial neural network works? And this is a crucial issue, right? There's a lack of reliability and explainability of many artificial intelligence algorithms. And then again, this is what we started doing, learning the dynamics of processes when it is not clear from physics. Can we build up, say, artificial neural network algorithms, then respect basic physical properties? For instance, if I have to approximate the density of a fluid, how can I guarantee that my artificial neural network will provide me a positive density, just to make an example? Or using uncertainty quantification to predict the success of the failure of the artificial neural network, and again, model quantization using variable floating point accuracy for training and activation. Those are some of the questions that still need to be addressed, and which will actually say provide better understanding of artificial neural networks. And let me conclude by saying which is the basic picture that I am that I want to address in those cases. I want to move toward say what can be called digital health or digital medicine, and we like to use these methods to have a better understanding of the physiology, right? Going from atlas to which are static or stationary, which are made by drawings, to a quantitative and dynamical atlases.
Yes.
We want to understand the human physiology and help doctors to better understand it. And also maybe in the future, to help students for having virtual medical training by simulating. You change one parameter, you change the pressure, or you change the mechanical characteristics of the myocardium, or you have a regurgitating valve that you can put in your system and see the way it changes the scenario. Or again, you have a coronary which is occluded and see the way the perfusion can be reduced. Then we want to address pathological scenarios. We want to improve the diagnosis, to possibly allow patient-specific treatments, and to have a better use or better fit of prosthetic devices that better account for the shape of a specific organ of a specific patient. And in the end, optimize the surgery. When you have different protocols for a specific pathology, try to see which one performs better for the specific patient at hand. So all those are examples of problems that potentially we, the mathematicians, can address by using methods like those that have, say, presented to you today, which try to reproduce, hopefully accurately, very complex physical processes that take place in our heart or in our body, generally speaking. And with this, I would like to stop and to close my talk, and of course, be glad to answer questions if you have questions.
Yeah, sure. Thanks so much. Okay, so yeah, thanks for the great talk. So it's a Q&A time, so please feel free to unmute yourself and then ask a question to Professor Quarteroni. Want to go first?
I'd like to ask for a question.
Sure, yeah.
Right. So it was really impressive talk. There's a lot of complexities, especially when you're talking about the coupling between the brain, the heart, and the lung. This seems a little beyond my level of complexity. So one of the questions is that because you show to simulate one heartbeat, it takes about 4 hours on a super large computer, like using parallel. So I think that's one of the limitations for the wide adoption of this technology. So do you think it will be ever possible that someone can just use their laptop to run a simulation, like a routine sort of simulation on someone's workstation? Is it possible, achievable? The other thing is that because you're saying it's a one simulation, 1 second of heartbeat take 4 hours. Do you think it's possible to simulate faster than real heartbeat, less than a second, so that you can, if you simulate faster than the heartbeat, you may make predictions more efficient? Is that possible at all from a numerical sort of point of view?
So, Pan, thank you very much for this question. It's very crucial and very, very important, actually. Let me try to be very clear here. It takes 4 hours for a single heartbeat when you use the complete physics.
Yes.
You remember the model, right? The complete model. And then if you want to go with the high accuracy and to simulate the complete heartbeat with all the variables, all the physical variables, it takes so long. Now, doctors typically are not interested on the whole process. They have specific questions. For instance, a specific question about atrial fibrillation, or about the perfusion of the coronaries, or again, about the behavior of the heart valve. So when you have those type of specific questions that you want to address, you can, this is what we did actually already. We use the physical models in combination with artificial intelligence to provide an answer to that specific question. We were not simulating the whole process. We just use those models that are important to get to give an answer to the specific question.
I see.
So you take the whole model, basically you switch off those models that are not really relevant.
Okay.
Right? And with the help of artificial intelligence to get reduced order models or to estimate the parameters that are really relevant, we can go to the level of few minutes on a laptop.
Okay.
We are not yet real time, but we go from, the 4 hours on the big supercomputer to a few minutes on a laptop. And I'm very optimistic about this. We need to improve the combination between artificial intelligence and physics-based models to further reduce this computational time. But I believe that this is feasible. Again, we are mathematicians. We are interested in addressing the problem with the highest possible complexity and accuracy. But then there is the real life where maybe the accuracy that counts is 10%, is not 1 per 1,000, you see. And because that's already helpful. And you are not interested in all fields, but just on some specific fields. And these help a lot indeed. So that's the way I think we have to go.
Yeah, thanks for the answer. And also I have another follow-up question, because in the end of your talk, you start talking about, for example, oxygen supply, ATP sort of consumption. So by coupling this respiratory or even the brain system to the heart, so that will be, I see, as a challenge for the cell models, because a lot of cell model itself developed many years ago, they do not have this capability to handle, for example, oxygen supply or ATP sort of dynamics. So how easy it is to replace some module, for example, some cell models in your integrated model? Is there a lot of effort in terms of coding, or it is quite straightforward using, for example, one of the LifeX library or saying, so we can just change or swap any model of interest quite easily?
That's a very good question. I have two different answers. The first one is, it is very easy from the coding point of view. The difficulty is to have the right model. So if you have a right model, we can easily integrate it into the complete picture. Mm-hmm. And actually, we are at a very preliminary stage. We made some effort with the when we had the COVID to try to have some preliminary, very preliminary models at the cell level to change. Let me just show you very, very quickly. I can still share maybe, and I'd like to go to a specific place. Yeah, for instance here, right? It's just a sketch. All right. So this is the place. This is the place where you have to change your model. You see the way the fourth generation is created in combination with the change of the ionic model, maybe, that you have at this stage here. So we know where to go. And right. If we know which model we have to use to account for the reduction of the oxygen, then the global picture will not change. And the global library will be there. So the real issue is often, as it often happens, is understanding. The more understanding we have, the richer will be our model. But injecting this new model into the global picture is easy. So we are very open to collaboration. If you have any specific application in mind, which I would say allow to use cell models that you have developed for some specific issues, and you like to see the way it could be injected into the global picture, and how at the systemic level this will produce results, please let us know. I mean, I'm very open to that.
Well, the top of my head is really the circadian sort of rhythmicity, how that play in the whole cardiac function, how the circadian rhythmicity can be plugged into your whole picture, sort of global heart model. That'd be really interesting, because heart disease, they have a specific time window to occur. For example, certain cardiac deaths, they occur 4 o'clock in the morning, some occur in the afternoon. So that's the timing can be related to the circadian rhythmicity. So that'd be one of the, at least my interest. Yeah, thanks a lot.
Great. So yeah, any other person? Yeah, please feel free to have a question.
Let me ask a little bit technical question, Alfio.
Yeah, very good.
So I was wondering if this if you have used any high order scheme in space and over time, so that could enhance the speed and efficiency.
I'm sorry, can you
for the time you have, you may use a high order time stepping method or high order method in space.
Okay.
So I was wondering what kind of scheme you have applied and so on.
Yeah. Thank you very much. Yeah, absolutely. Well, as we are saying, there are different processes that take place at different scales, and they have different characteristics. For instance, for fluid dynamics, Navier-Stokes equations, we typically use second-order time stepping and low-order methods. Say first order for in space for pressure and velocity plus stabilization. For electrophysiology, we have very fast propagating waves with very sharp fronts, and there we use higher order methods, both in space and time, because we want to reduce the dissipation error and the dispersion error. So we try to adapt the methods to the different physics, and also to use delta T, which indeed accounts for the different scales. Typically, we use, say, delta T equal to 10 to the power minus 3 seconds for the mechanics and for the fluid dynamics, and 10 to the power minus 4 seconds for the electrophysiology. Which means 10 to the power 4 time step for every heartbeat. But we know that we have to be specific to the specific process we are dealing with, because it's a multi-scale with different type of eigenvalues and the different stiffnesses. So the condition number of the different pieces are different, and we have to account for this. And that's very crucial.
All right, thank you.